Problem number 23. A spring has a length of 1 meter when there is no tension on it. The spring then stretched between 2 points 10 meters apart. A wave pulse travels between the two end points in the spring in a time of 1 second. The spring is now stretched between 2 points that are 20 meters apart. The new time it takes for a wave pulse to travel between the ends of the spring is closest to. Solution for problem number 23. First, let's write the expression for speed of a transverse wave in a spring with a tension T. This speed equals square root from tension divided by linear density, which is mass over length of the string. In our case, the length is 10 meters, and if we stretch it by 20 meters, we increase tension twice. But the same thing happened to length. We will increase length twice. And finally, we will get tension in a string with a double length will be doubled and speed of wave will be doubled. So it means that total time to travel must be the same with the initial stretch, and answer is C. That was solution for problem number 23. Problem number 24. A ball of mass m moving at a speed v collides with a massless spring of a spring constant k mounted on a stationary box of mass big M in free space. No mechanical energy is lost in the collision. If the system does not rotate, what is the maximum compression X of the spring? Solution for problem number 24. Because we don't have any energy loss, we can use both energy conservation and momentum conservation. When we have maximum compression, it means that both mass and box have the same velocity. It means that we can write equation for energy conservation, that initial kinetic energy 1/2 mv square going to final kinetic energy with speed v prime 1/2 m small plus m big multiplied by v prime square plus potential energy of compressed spring, which is 1/2 kx square. And also we have in this moment momentum conservation. We have mv equal m small plus m big v prime, and from here we can find what is v prime. V prime equal mv over small m plus big M. Now we can insert this v prime in this equation and find that kx square equal mv square minus this expression, which is finally we will get small m multiplied by big M divided by small m plus big M v square. And from here we can find that x equal v multiplied by square root from small m big M over small m plus big M k, which is answer A. That was a solution for problem number 24. Problem number 25. A planet orbits around a star S as shown in the figure. The semi-major axis of the orbit is A. The perigee, namely the shortest distance between the planet and the star, is 0.5 A. When the planet passes point P on the line through the star and perpendicular to the major axis, its speed is v1. What is the speed v2 when it passes the perigee? Solution for problem 25. Here we can use two main formulas. One formula is the parametric formula for trajectory in polar coordinates, which connect distance with the angle. This formula is distance r equal to r0 over 1 minus epsilon cosine theta. Here theta is the angle between x-axis and the direction to this planet, and epsilon is eccentricity, and r is 0, that's distance from star to planet, where this planet is on a perpendicular to major axis. Now we know what is semi-axis and what is perigee. So we can count from this formula what is eccentricity and what is r0. For angle equal 0 degrees, we have maximum distance, which is apogee, and that's equal to this expression, cosine theta equal 1. And in perigee, we have angle equal pi, or 180 degrees, and the formula is this one. Now we can divide the first formula with the second formula and find what is eccentricity. From here we can find that epsilon equal 0.5 and r0 equal 0.75a. So we just constructed all what we need for the next step. Next step, we can use a formula for total energy, which is a well-known formula. Total energy for any elliptical orbit equal negative g multiplied by mass of planet, mass of star, and divided by major axis 2a. And now we can use this formula for point P and for perigee. For point P we have this expression that the total energy equal to kinetic energy plus potential energy in point P. And from here we can find that Gm over A equal 3/5 V1 square. And this result we can use in perigee point. In perigee point, again, we have total energy equal kinetic energy plus potential energy, and from here we can find that V2 square equal 3 times G big M over A. It means that V2 equal this expression, which is answer A. That was a solution for problem number 25.